Hello kittens. Ready for something new? Let's go. Take a look at the screen. Our character can walk wherever it pleases. Neither trees nor cliffs hinder it. Let's fix that. I suggest creating boundaries for movement using math and logic. We won't involve physics, that's too simple. So, let's recall our coordinate system. The center of our scene coincides with the center of the coordinate system. Let's move the character to the extreme position it should not cross. And in the right panel, we'll check the coordinates. We see that the extreme positive coordinates are 6.5 meters. From this, we can conclude that the allowable values for the character's movement on both axes will range from -6.5 to +6.5. Now, let's create a right boundary for the character that it won't be able to cross, even if it really wants to. We need a logical branch, player input. At this point, we move the character to the right, and now nothing can stop it from moving right infinitely. So, let's check where the object is right after it takes another step towards infinity. To create this check, we need a gate block from the logic group. This block performs a check on a specified condition every time it receives a control signal. If we connect it after the object's movement, the check will be carried out after each step is taken. That's what we need. By default, the block has the equality comparison operator selected. You see those two green inputs? The block will compare these two values. For example, if both inputs receive a value of 5, the check will yield a positive result, and then the true output will trigger. The code connected to this output will be executed. However, if the incoming values are different, for instance, 5 and 2, the check will result in false. Then the second output labeled false will trigger, and all the code connected to it will be executed. Now, let's express in plain language what we will be checking, what we will be comparing, and what to do after the check. The algorithm is straightforward. If the character crosses the boundary, it must be promptly returned to the boundary. Now, let's take the phrase cross the boundary and translate it into the language of mathematics. It will sound something like this: if the current position of the ship on the x-axis is greater than 6.5. We need to translate this quite specific expression into node language. So, our comparison consists of 3 parts: the current position of the ship on the x-axis, the comparison operator called greater, and the numerical value of 6.5 to which we are referring. Let's give it a try. We can obtain the position of the ship at any given moment with the getObjectLocation block. We can isolate the x-axis with a separate block. Connect this combination to the first input. Choose the greater operator from the list. As for the fractional numerical value, we can connect it from the float block. That's it. The condition is created. If our character's x-coordinate suddenly becomes greater than 6.5, then the true output will trigger immediately. Now, let's formulate our task. What do we want from the character in this case? And we simply want it to teleport back to the boundary, immediately, in the same tick, as if nothing had happened. For this task, the setObjectLocation block is the most suitable. This block works with absolute values. We can't enter fixed values directly into the block because fixed values would only be for the x and z axis. However, the y-axis will be different each time, and we must preserve it. This is where the vector block can help us. Enter 6.5 for the x-axis, 0.5 for the z-axis, and connect the y-axis to the current y-axis value. We can obtain this from the separate block. but it's better to duplicate this block and connect it to the values from the getObjectLocation block for neatness. The moment of truth. Let's run the game and try to overcome the invisible barrier at full speed. We can't do it. That means we're on the right track. Let's return to the code and tidy things up. These 4 blocks constitute the condition. I'll color all conditions in green. Label the frame if right border. The remaining 3 blocks work with coordinates, so we'll color them in that familiar blue. Let's copy it and paste it into a new frame. Label the frame back to right border. Now we need to copy this section of code 3 times and connect it to each direction: forward, left, and backward. And now, let's set up the remaining boundaries. Take, for example, the forward direction. This is the upper boundary, and positive values along the y-axis. Change the labels on the frames. Now they are if top border and back to top border. Change the x-axis to the y-axis in the condition. So, the condition now sounds like this: if the current y-coordinate is greater than 6.5. In the blue frame, we also need to change the axis. Now we need a fixed value, 6.5, along the y-axis, while we leave the x-axis unchanged. Transmit what we have obtained. Moving to the left. Again, it's the x-axis, but this time with negative values. Now the condition should sound like this: if the current y-coordinate is less than -6.5. So, we need to select the less than comparison operator and change the value in the float block to -6.5. In the vector block, change the value to negative as well. Don't forget to rename the frames. The last direction. Moving backward. In the green frame, change the axis to y. Change the values to negative. Change the comparison operator to less. In the blue frame, keep the values along the x-axis. Enter -6.5 along the y-axis. Now, if you didn't make any mistakes, when you launch the game, you won't be able to cross any of the boundaries. Check all directions. If any boundary behaves inadequately, trace the key causing the issue. Go back to the code and think about where the error might be. Debugging is a very engaging and creative process that often takes much more time than writing the code itself. I hope everything worked out for you. That's it for today. Don't be bored. Goodbye for now.